Cool. Hi, everyone. I feel like I'm looking at the brave ones here based on the weather that we're seeing outside. But I'm glad everyone came. And this is a session that I'm sure you'll remember for days. So this is the first Google developer workshop that we've had in ages. I'm just thinking about like the sad days of COVID. So this is like very first time. So I'm glad everyone took time to come and join us here. So let me first just do like a brief intro, but I'm pretty sure every one of you like knows what GDG Cape Town is, but I'm just gonna do like a reminder. So basically we are a group which does like these meetups, developer meetups. We are supported by Google, but we're independent. So we do meetups on different topics, mainly Google related. You think about Firebase, think about GCP, UI, UX, and ML as well, which is a related topic for today. So we do sessions every month. So we had a session last month. There's another one, and we also have our annual bigger conference, which is the DevFest. So you should come to that as well. So all the speakers are volunteers. So be kind and also ask nice questions. And then we are taking suggestions on talks. So if you have a talk or you wanna deliver a talk yourself, or you know someone who could be perfect for this session, so you can like talk to one of the organizers for that. So we have sponsors for this event, but before that, let's talk about the organizers. Currently, it's myself, Siso, the third one, with Ugo, Jessica, and Onesmus, who are the volunteers for who are setting this thing up. But then we also have other people in the background as well. For example, the team at AXO, who's done a perfect job. So the way you can get in contact with us is mainly via Twitter, email, Slack, and also you can just ping one of us, the organizers. We do have a code of conduct that we're trying to enforce, but everything's in the QR code if you scan it. But then there's just one thing which I want to enforce, like that, like alcohol for minors. Let's try and prevent minors from drinking alcohol, or if giving alcohol to minors. That's something that we've seen before, but let's prevent that. So who made this event possible? So we have like AXO, who provided the venue. It's perfect, as you can see. And then we have Google as well, who's providing support, and we have JetBrains. So thanks to our sponsors. So if you know someone would be perfect at sponsoring these events, still ping us, the organizers, or maybe yourself, you want to sponsor. So today's agenda, it's quite simple. You've seen it. We have the arrivals, which has happened, and the tea at the back. So we're gonna go to, afterwards, we have this welcome. Then the next one will be the keynote, which is gonna be presented by our speakers. And then we have a small break. Then we're gonna head to like the actual sessions now. We have sessions by Gesa, by James, John, and Ugo. They're all noted here. So we're gonna try and divide them into different sections. We have these rooms here that we're gonna try and split people. So because all those sessions are gonna happen at the same time. So it's a matter of like checking which session you wanna attend, or you can even move between the sessions. But then when you get to this area here, we're gonna explain it further after the short break, so you don't have to worry about it. And then after that, we're done, and then we have some socializing that's gonna happen. I hope you really enjoy the session. Okay, thank you. Okay. So the next session now will be the keynote. So I'm just gonna hand it over to Ngesa for who's gonna be our main first speaker.
Okay. Good morning, everyone. I hope you guys are enjoying the event, though we're just starting. I know it's very cold, but I'm happy to see that all of you are paying attention. because almost every single thing you're going to do today is going to depend on attention, and including the things you're going to work on, the tools you're going to work on. And I also know that you've been probably using ChatGPT, you've been using Gemini, you've been using all these chatbots. But behind it, the key thing is depends on this paper called Attention is All You Need. So today, as we go through all these sessions, probably attention is all we need, because this paper contains how large language models, and that large language model is what is behind the Gemini that you're using. Behind what you're typing on is a large language model. And the paper contains how large language models can be taught to pay attention to a certain words of some kind of input sequence, the same way that a human being can also pay attention to those words. So again, attention is all we need. And by the way, this paper is by Google, and it's like almost all the large language models depends on it. And of course, there's Gemini. You've heard about ChatGPT. You've heard about Llama. You've heard about all these different chatbots. But behind it, there's one thing called large language models. Of course, some of them are private. Others are open source. Private ones include ChatGPT, Palm, Gemini, and all that. They're all private. Other open source, like Llama, for example. Today we have Gemma. How many guys have played with Gemma? Nice. Yeah. And by the way, you can even integrate Gemma with Keras and use it. I will share some links if you want to, if you want to try to use them. But today I'm going to focus on, of course, I know you guys have heard about AI, so I'm going to find a way in which I move you from AI to Gen AI to Gemma and Gemini, or rather to Gemini. And then we see how all these things relate together, so that at the end of it, you don't confuse all of them, but we know how they're all related together. So we've heard about AI, we've heard about machine learning, but what's the difference? Every single day, we have people using them interchangeably. Some people use AI for machine learning, there's deep learning, but we just use them interchangeably. But is there a difference in them? Is there something that differentiates one from the other? And also, behind this, also there's generative AI, which is now a buzzword. Everyone is talking about it, but what does it mean? Okay, so if you have something that behaves like a human being, if you build something that behaves like a human being, then you can say that's an AI. And by behaving like a human being, I mean, if you have something that can act, can be able to sense the environment, what's happening in the environment, the way you're seeing me, you can sense the environment, and you can also be able to reason from what you're sensing. You can make sense out of what you're seeing, and then act after reasoning. And then even beyond that, be able to adapt from that, then that's an AI. If you can build a system that can do that, then that's an AI system. And by acting, and beyond that, it's just an umbrella that covers all these other ones. That covers the machine learning, covers the deep learning, and all that. And beyond it, you have machine learning. And with machine learning, you're basically having something like a function, or I would say an algorithm, which is a big term, but you could say it's just like a function. And this function, if you give it more data, if you provide it with more data over time, and you notice that its performance improves over time, then you could say that is machine learning. Just a function. Of course, you guys are used to y is equal to mx plus c, or the guys in machine learning, y is equal to w, x plus b. So if you have that function, and then its performance improves over time, you are changing the values of the gradient, or you're changing the values of the bias over time. And when you change that one, you're getting a better and accurate kind of function, then that's machine learning. But machine learning, of course, falls under artificial intelligence. But if you combine more of this function to a point where you have something called neural networks, and then add more data to it, and by more data, you add a vast amount of data to it, then you're going to have something called deep learning. So that's the difference. So you have AI, which is the umbrella. You're just trying to train a machine to behave almost like a human being. And then you're having machine learning. You're just having, you try to model something. You're trying to model a distribution. And the more you model this distribution, the more you give it more examples, then if its performance improves over time, then it's machine learning. So that's the difference. But machine learning gives computer the ability to be able to learn from the environment without explicitly programming it. And what that means is, in traditional programming or classical coding, you used to have rules and then data. And then the rules model the data to a point where you're now able to get answers. But this is different from machine learning, where you just have answers and then you have data. And what I mean by that is that I can have a picture of this room, and then I say I have maybe human beings in this room. I label what is in this room. It's that I have the data, the pictures of the room, and then I have the answers. If I have both of them, then in some way I can be able to model or have a distribution that represents the photo of people in this room, and then I have answers for it. At the end of it, I'm going to get rules from that one. If I have that one, then I'm going to have a machine learning, which is different from classical programming. And of course, the different types of machine learning, you have supervised learning. There's a supervised learning as well. But supervised learning is where you're having the photo, and then you're having a description of the photo or an answer to the photo. And ideally, just trying to have data points that have known outcomes. And in unsupervised learning, you're going to have just a photo of people in a room, but you don't have answers to it. You just have a vast amount of data, or you just have data somewhere, but you don't know what's in that photo. An example I usually give people is that imagine that you have people in this room and they're sitting in different. There's a way that they're sitting. You could get friends sitting together, or people from the same class sitting together, or same school, or same locality sitting together. You may not know that. You may not have answers while they're sitting together, but in some way, if you analyze it, you may realize that these people are sitting together because of some reason. These other people are also sitting together because of another reason. The other people are sitting together because probably they've been in this community for a long while. So that way, you can be able to classify different people in different parts of the room without even knowing why they're sitting together. Okay. Okay, so probably if you're an owner of a restaurant and then you want to know the type of food that you could serve, you may have historical data of the bill amount and how much different people are being tipped in a particular place. And then in supervised learning, the model can learn from past examples to predict the future values. For example, on this other side, you can see that the model uses the bill total amount to predict the future of the tip amount that could be based on whether an order was picked or delivered. But in unsupervised learning, you're going to use past examples to predict future values, and you're going to, in some way, discover what's in the data, and just look at the raw data, then see where things naturally fit in different groups. And for machine learning, again, you have this simple graph where you have an input data, and then you come up with a model. So the first thing you do is that you have this example, and then you try to build a model or try to make a guesswork. Then once you make a guesswork, you try to figure out how is this guesswork far from the true answer. I have these pictures. I think that probably they're of whales, but are they whales? Is there some ground truth somewhere? So you figure out how the answer you're trying to give or the guesswork you're trying to make is different from the ground truth. And then you get that difference. You can compare the two and get a difference, and you can call it an error or loss function in machine learning. And then you figure out what is it that I can do to ensure that I'm able to tweak all this to ensure that I'm able to reduce this difference, the predicted value with the expected outcome. Of course, when I add, by adding more data to it and with training it for a certain period of time. So here's another example where you have values of X. You have 1, 2, 3, 4, 5, 6, and 7. And then you also have values of Y. And for every value of Y, for every values of X, you have a value of Y. For example, you have 1, you get 7. You have 2, you have 14. You have 3, you have 21. If I go to 8, what will I have for Y? Yeah. If for every values of X, I'm having 7. For values of 2, I'm having 14. For values of 4, I'm having, yeah? 40? 46. 56. How did you guys get that? Yeah? Multiply of 7. Yeah, that's correct. So you could see that I'm giving you values of X, and with time, if you are able to see the values of Y with time, if I add you more data, you can figure out what I can add to X to give me the next number. You can figure out that, in fact, the weight that you're having or the gradient that you're having in all this is 7, and therefore if I multiply that 7 by the next number of x, I'll get the values of y. So in some way, you are always trying to add more data, and then with more data, you can be able to get the values of y. And sometimes maybe the answer is not even 7, maybe it's 6.99. You may never know if the answer is truly 7 if I give you more data. But at least right now, that answer gives you a closer answer to what you're having here. But that's the essence of machine learning. You have data, and you have values. You have data. You have answers, and you're trying to approximate that x as a function of y. And if you see what you're having at the end of it, you could see that you have this high school. I don't know if you call it high school or secondary here, but you have this high school equation where you're having a gradient or mx plus c or wx plus b is equal to y. And it's something that we're calling a linear unit, because what you're having here, if you give it an input, you're going to do some processing to the input. You're going to do some multiplication. You can see w times x, some multiplication, and then some addition to the bias or the y-intercept that you're having. And then you're going to get an answer from it. And you could see that you're having an input, then you're doing some processing, then you get an output from it. And the way it works is almost similar to how the neurons in our brain works, because also in our brain, you're having inputs. You're able to see that I'm here. You're able to touch things. And when you touch them, you're getting these inputs to your brain. Then there's some processing that is being done in your brain. At the end of it, you could say, I can feel that there's a laptop here. I can see that these people are here. So you're having input to your brain, you're doing some processing, and then you have an output from it. And because they behave in a similar way, it's fine. It's okay. All right, so we're here, and I was telling you that you have data and you have answers. And if you provide more data over time, you get an answer like 7x, for example. And what you're trying to do is just you're always trying to fit this formula. You're always trying to approximate y as a function of x. And in this equation, you can see that you have input, then you do processing, then you have an answer. And this works in a similar way as your brain, where you see people do the processing and then get an answer from it. And because it behaves that way, that linear unit, because it behaves like a neuron, you could say that what you're having is a neuron. And if you have neurons combined together, then you're going to have a neural network. And what you're trying to do is that you're trying to always find a distribution or map a distribution or find an equation. And what you do is that initially you make a guesswork. You make a guesswork of what you think. You make a guesswork of an answer. Then, for example, if you have this line here, and you could see that you have the true values, the red ones, and then you have the predicted value, the black line, and you could see that there's a difference between the dots that you're having and the black line that you've predicted, the guesswork that you made. But your goal as an ML engineer is to ensure that what you're trying to predict is as close as possible to the true answer or the ground truth. And therefore, you need to get the difference between what you're predicting and the ground truth that you're having. So here, you could see that you could decide to use different methods to get the difference. For example, here, you could decide to probably subtract this number from this one. I mean, all the dots from the black line, subtract them. And then you could decide to get an absolute value of those numbers, because if you add this one to this one, they may cancel each other. But you don't want them to cancel each other. You want them to you want to get the difference that you're having in between the ground truth and what you're predicting. So you could decide to get the absolute value, then sum all of them, and then get the difference, get the absolute value, then sum all of them, and you could end up with something called mean absolute error. Or you could decide to get this number, get the difference, square them, then sum all of them. You could end up with mean squared error. So there are different ways in which you can get the error, and the different frameworks give you different ways to get that difference. Then once you get the error, then you need to figure out what is it that I can now do to be able to reduce the error, because now I have the error. So and then that means that your goal is going to be to minimize the loss function, because that error is called the loss function. So what you could do is that you could draw this graph. It looks like it's complex, but you could just have this graph. If you have this graph, because you squared the function that you're having, you most likely are going to have this curve phasing up, any squared kind of function. So once you have that curve, then probably at maximum error, you're somewhere here, but your goal is to go to this particular point. And this particular point, you'll be able to get the best sets of weights or the best sets of gradient that gives you the least amount of loss or the least amount of this function here. So you're here and your goal is to figure out how do I move from this point to this particular point. What you could do is that you could get the gradient at this point. Then once you have the gradient, you could go the negative side of that gradient. And if you go that way, it's like you are on top of a mountain and you're on top of a mountain, you're blindfolded, and you're trying to figure out how to go deep the valley. So I have a diagram here, and you don't know where to jump and how to move. And when you go down, it's like you're descending down the hill. So they're calling it a descent. So it's a gradient descent. And if you don't know like how to move, or you're moving in a random way, you could say it's a stochastic gradient descent. And that's one way in which you could move down the hill and even reduce the error. So that's a way in which you could move your prediction that you're making or the guesswork that you're making to go as close as possible to the ground truth. Or you could move all those red lines to move as close as possible to the black line that you're having. So you could see the person is going down the hill, and of course, there are different ways to go down the hill. You could have a starting point, and then you go negative side of the gradient, and if you do that way, you could see that, you see the way the black line moves to the red line, that's how it goes. And if it goes that way, you'll be able to reduce the loss that you're having, tweak your weights, and then eventually have a function that correctly map what you're trying to predict. So I also have another one here where you could have something called forward propagation. And that forward propagation is basically the process of passing inputs through a neural network. You're trying to do the multiplications. You're trying to do the processing. You're trying to multiply the weights and the values of x and the bias to get an answer. If you do that fast multiplication, you're going to have a forward propagation. But once you have the forward propagation, then you need to go get the error, then do the backward propagation as well. And when you're doing the backward propagation, ideally what you're trying to do is that you're trying to tweak those sets of weights to be able to move from the number that you had. For example, when I ask you what do you think represents, how will you map the values of x to the values of y? Someone said 6, then someone said 7. So you could see that even in the room, we're trying to tweak the weights. We're trying to move from 6 to 7. And by the time we're at 7, we're able to have a number or a weight that helps us to map y as close as possible to x. And when you move from that 6 to 7, ideally what you're having is the backward propagation. You're trying to adjust those weights. And in some way, you could say that probably machine learning is just adjusting. Machine learning or deep learning is just trying to adjust these weights. You're just trying to do matrix manipulation, but at the end of it, you're trying to adjust the weights and the biases that you're having. And if you have those neurons, if you combine them together, a group of them can be able to form something called a layer. And those layers can be connected to the other. For example, that equation that I showed you, you could represent it as what I'm having here, where you are having x0, x1, and 1. And then if you have all the layers, all the previous neurons connected to the next neuron, then you're going to have something called a dense layer because all those neurons are connected together. And if you're having like a bunch of those layers together, and also you're having like a vast amount of data, you're going to end up in something called deep learning. And while machine learning could be a broad field that encompasses many different techniques, then deep learning is just a type of machine learning or AI that allow them to process more complex patterns from more than the one for machine learning. You could see here, you're now going to have more neurons together or more functions connected together with some input layers, some hidden layers, and even some output layers. So, and then again, also, beyond machine learning, you're also going to have deep learning. You're also going to have generative AI. And generative AI is just a subset of deep learning. And generative AI is where you're going to have a function that's trained on a vast amount of data. Let's say a bunch of images from people here, to a point where it's able to map the distribution to a point where it can now be able to create a new kind of image on its own, either an image or a text or a code or a function. Because you've been able to give it a vast amount of data, it's been able to map that distribution to a point where now it can be able to come up with a new one on its own. So, and I tell you that beyond the deep learning, you're also going to have something called large language models. And large language models are just neural network that are trained on a large data set. We move from a linear unit to what a neuron is, and then you move from a bunch of neural networks. So if you have neural networks that are trained on large data sets, then that's a large language model. And when I talk about large data set, I mean trillions and trillions of data. I mean trillions of texts, trillions of images, trillions of audio, trillions of video. And at the end of it, you're going to have a model. You're going to have a function, or let me just say a function that models the frequency distribution of the text, the frequency distribution of the images, the frequency distribution of the video from a variety of sources, to a point where it can detect complex patterns from all these sources. And if you give it a given input, for example, here, if we say, for example, it's raining cats and something, then on its own, the model is going to figure out that the next answer is it's raining cats and dogs, because you already have a frequency distribution, or in the data set that it was trained on, it's so used to having the next number be cats and dogs. That's what it sees on the data. So it's going to give you it's raining cats and dogs. And you also have the large part in the large language model. And if you talk about the large part of it, then you're talking about the training data. And you're going to have trillions of tokens, trillions of data that you're having. And then also you're going to have parameters. So the large in it, you're going to have like 340 billion parameters. Other guys are having 1.7 trillion parameters. These different models, if you check on them keenly, if you check on Gamma, you check on Llama, you check on Gemini, one of the key things you're going to talk about is parameters. And they're in the billions and the trillions of itself. So those ones are what forms the large in the large language model. You also have compute resources. Some people are using TPUs and a bunch of others. And then, of course, Google also has Gemini from it. And Gemini is where is it? Okay. And Gemini today is the most powerful, capable model across the images, across videos, across audio. And today, if you take 60 different human beings, or if you take 60 different fields, from medicine to law and all this, and then you get the best human being in all those different fields, then Gemini today will outperform all those humans in those different verticals, the best of the best in those different verticals. And they're saying that it can score above 90% in those different subjects. And so large language models ideally refers to the large general purpose languages, models, that can be pre-trained and then fine-tuned for specific purposes. And when I talk about pre-training or fine-tuning, what do I mean? So you could imagine that you're having a dog, and this dog, you can always give it different instructions. You could tell the dog to sit down, you could tell the dog to come, you could tell the dog to stay. So you have different commands that you could give to a dog or train the dog on. And if you give it these different commands, then on day to day, it could be sufficient for them to do what they're doing. But if you need a special service dog, like let's say a police dog, for example, then, or a guide dog or a hunting dog, then you may need some special kind of training for this kind of dogs. And this idea is almost similar to what large language models are. These models are trained for general purposes, but if you want them to solve a particular problem, if you want them to solve, let's say, a classification problem or question answering problem, or even document summarization, then you may need to give them a special kind of training, the same way that for a police dog, for a guide dog, or a hunting dog, you also give them a special kind of training. And the model can then now be trained to solve a particular problem in different fields, like in retail, for example, in finance, in entertainment, because now you've been able to give it a special kind of training to what they're having. And there are three different kind of large language models. You could have the generic language models. You also have the instruction tuned models. You also have the dialogue tuned models. So these are the three kinds of large language models that you can be able to use. And each of them needs prompting in a different way. So you don't just use all of them the same way. So the three ones need prompting in a different way. For example, genetic language models predict words that are based on the language in the training data. And the next token is always based on the language in the training data. For example, here you have the cat sat on, then it needs to figure out what the next answer is. The next answer is the cat sat on something. So the next keyword should probably be the, and you can see that the is the most likely keyword, and you could almost think of it as autocomplete in search, the way it works. So that's the first one. Then the second one is the instruction-tuned language model. And this type of model is trained to predict a response in the instruction given the input. For example, if you want to do summarization, let's say summarization of X, or generate a poem in the style of X, or give me a list of keywords based on semantics of X. So this one is different from the other one because it's more of instruction-tuned language model. You could also have examples and answers. Then you show the model on how it should give you the answers. So if you have a list of examples and a list of answers, and you can show the model how you're getting your answers, and then at the end of it, it's able to give you answers according to how your data was, then it's more of an instruction than the other one, which is just autocomplete. And of course, working with them or how you give them prompts is different. So here's an example, classify text into neutral, negative, and positive. So you have the instruction, then you have the output indicator. Then the last one is the dialogue-tuned language model. This model is trained to have a dialogue by the next response. So dialogue-tuned model is a special case of instruction-tuned model where requests are typically framed as questions to a chatbot. So dialogue tuning is expected to be in the context of longer or back and forth conversations, and it typically works better with natural question like phrasing. Then these deep learning models, they can be divided into two different types. You could have the generative kind of model, and then you could have the discriminative kind of model. So the initial one that we're describing was more of a discriminative kind of model. And discriminative model is a type of model that is used to classify or predict. The old ML that we're used to, I could call them classical machine learning that we're used to. And then you have the generative kind of model where you're able to generate new data instances based on the distribution that you have. So initially, you could have, let's say, images, and then you have answers to the images. It's more discriminative. But if you tweak all this so that instead of providing an image, you provide a text or the answer that you're having, or you provide what you're calling a prompt to it, then it's more of generative. And those are the two key ones. So I have an example here. And you could see that the discriminative models could learn the conditional probability distribution of let's say Y, for example, given X, that this is a dog, and it can classify that dog as a dog and not as a cat. And then on the other side, on the second one, you have a generative model that learns what you're calling a joint probability, or you could say conditional probability of both X and Y. And then it can tell you if this is a dog, and then generates for you a dog. So if you check on these two, generative model can generate new data instances, while discriminative model can differentiate between two different kind of data that you're having, as you can see on the image. So here's another example where if you see on the top image, you could see a traditional machine learning model which attempts to learn the relationship between the data that you're having and the label. While in the bottom one, where you're having the unstructured content, the bottom image shows that a generative AI model attempts to learn patterns on content so that it can be able to generate new content. It just maps the frequency distribution of what it has to a point where it can now be able to generate for you new text or new video or new image. Then here's another example that can help you differentiate between what is a Gen AI and what is not a Gen AI. So you could say that it's not a Gen AI when the output that you're having, and that output is Y, if you remember our first equation, is a number or is a class or is a probability. And you could also say that it's a Gen AI, what you're having at the bottom, when the output is a natural language. It's a speech, it's a text, it's an audio, or it's an image that you're having. Okay, you could take a photo. But the question just remains the same, just that equation that you had in high school or secondary school, where you're having the values of Y, which is an output, and you also have the values of X, which is the input. Of course, you're always trying to approximate Y as a function of X. And again, it's a Gen AI if the output that you're having is a natural language, it's an image, is an audio, or is the values of Y that you're having. And it's not a Gen AI when you're having a number, which is discrete, or you're having a class, dog, cat, or you're having a probability of what you're having. Then another key concept is tokenization. When you're trying to build all these things, I think there's a tokenizer. In fact, even the labs that you're going to have today, you're going to get a place where you're going to have tokenization. And large language models receive text as input and produce text and output. Usually, what you're trying to give the model, or what the kind of prompt that you're trying to give the model, can be converted into something called a token. All these numbers that all these words that you're having, they can all be converted into numbers. So if you're able to convert all these words into numbers, you're just trying to tokenize the number. I mean, the prompt that you're giving it to it. So it plays a key role. And it's essentially a chunk or text that can vary in form of length and typically consists of sequence of characters. But the primary job is to break down the input text that you're having into arrays of tokens. And then once you have these tokens, they can now be further be taken into indices, into integers, into numbers that you're having. For example, here you can see that if I put what is a token, then it can give me that in that entire word, the value for it is 5. Then the traditional machine learning model learning process can take code and label data to build a model. And depending on the use case or the problem, the model can then give you a prediction or classify something, or even cluster something. And if you remember in our first slides, those are some of the key things that the classical ML does. You could do prediction, you could do classification, you could do clustering for unsupervised learning. For example, the example that I gave for the room, where you guys are in the room and there's a way that you're sitting, and I don't know how you're sitting, but probably there's a reason why he's sitting here. Maybe he's sitting here because you want to check on all these ones. Someone is sitting there in a group, maybe because they're GDEs. Other guys are sitting there because probably they're from the same school. That way, you're able to cluster them without even knowing why they're in those groups. And then on the other side, the generative AI process can take training code, label data, and label data of all types, and then be able to build something called a foundational model. Then this foundational model can then now generate new content that you'd want to have. You can now generate, it can take text, you can take code, images, video, and more, then generate kind of new content from it. So we could say that generative AI is a type of AI or artificial intelligence that creates new content based on what it has learned, or based on the existing content. And the process of learning from existing content is called training, and the result of it is called creating a statistical model, or creating a function, just to make it simple. To a point where, when given a prompt, Gen AI uses this statistical model or this function to predict what an expected response might be on generating a new content from it. So it learns what you're calling the underlying structure of the data, and then can be able to generate new samples that are similar to the data that it was trained on. It will be able to learn, if you see all these things, every single thing you give to the function is going to be converted to a number. That equation at the end of it is going to be a number. So at the end of it, it's going to have a frequency distribution of the data that you've given to it, be it text, be it image, or be it video, to a point where it's able to know the underlying structure of all this. It's able to have a general equation that maps all these things, to a point where now it can be able to generate for you new content from it. And you can have different kind of model. You can be able to not just have images, but also have videos as well. So large language models can have a combination of text in the form of natural language and any other type of generative AI. And they can take text as an input, and then can give you text as an output. Others can take both text and images as an input, then gives you text as an output. Okay, and so for example, here you could see that you're having an input text, and then you can be able to have output text and also another image. If you have, for example, on this on the second one, you can have an image, and then you're able to have things like super resolution and image completion. For video, you can even at the end of it end up with animations, so which is being generated. So in this other example, under the output text, you can have questions and answering, which has been generated, and then a generated language model can take text as an input and can output more text, an image, audio, even decision. So here's an example. For example, for Gemini, that I just did a screenshot of it. You could say, what is the meaning of life? And then it could be maybe an ambiguous question, but still it can be able to give you a context answer and then show the highest probability of the response that you're having. So it can give you maybe 3 of them as a response to it. And then, of course, the power of generative AI comes from something called transformers. You remember the first paper that we talked about? It comes from something called transformers, and it was produced in 2018. And at a high level, you could say that a transformer model consists of something called an encoder on the other side, and then also a decoder. And the encoder encodes the input sequence and passes it to a decoder, which then learns how to decode the representation of a relevant task. So one side an encoder, the other side you're offering a decoder to it. But I want to go deeper into transformers. But also these transformers, they are really good. They help us to be able to create a frequency distribution, model something. But at the end of it, sometimes they run into problems. And one key problem that they run into is called hallucinations, where out of nowhere, this model can be able to come up with grammatically incorrect output or nonsensical answers. You could say nonsensical answers, and they can be caused by a number of factors that you're having. It can be caused probably by when you don't have enough data, or when you have noisy data, or when you have dirty data. The model is not given enough context, and the model is not able to have enough constraints to know how to give you the answers. So hallucinations can be a problem for transformers because they can make the output text difficult to understand. They can also make the model more likely to generate incorrect and even misleading information. And of course, there are different model types. You can have text to text, and text to text is where a model takes a natural language input and then produces a text output. These models are then trained to learn the mapping between pairs of different text. For example, you could learn how to translate, let's say, Xhosa from Zulu. Or you can also have text to image, where the model is trained on a large sets of images, and these images are captioned with maybe a short description. And then an example could be something called a diffusion model. If you guys have heard about diffusion models, that can be able to achieve that. You also have text to video, text to 3D, where text to video models aim to generate a new video representation from just a text input. So the input text can be anything from a single sequence to a full script to an output video that corresponds to the input text. And then today you can also have text to task. And text to task, the model is trained to perform a defined task or action based on the text input. And of course, the different use cases for AI today, you have text, you have code, you have images, you have speech, video, 3D, and even the others. And there are a bunch of use cases. And of course, the fastest way to get started is by using the Google AI Studio. And in our upcoming sessions, we'll show you how you can get started from Google AI Studio to Colab and the other ones. So yeah, I think that's it for now. Thank you for listening.
Thank you very much. So that was a lot to take in, but it was a really good session. Thank you very much, Ngiasa. We do have space for 2 questions. So if you have anything that you want to ask, there is space for it. We're going to set up for the next session with James. Yes, certainly. So is there anyone who has a question?
So the entire point of this whole talk is just to introduce you to the workshop you will have. I'm sure most of you have heard this talk somewhere on YouTube or somewhere else. The idea is not to bore you. The idea is to lay the groundwork, because he would facilitate some of the workshop you would have. So just makes the transition very smooth. So if you have any question right now, you can always ask him, and they will take it.
Hello, everyone. My name is Audi. Probably I have a question, but probably the wrong place to be asking, or the wrong person to be asking this question. But it involves about privacy. So these AI models require, like you said, a lot of amount of data to train, and some of this data will be gathered from scraping the data from websites online. So how does Google or any other these companies that are making groundbreaking technology like AI, like generative AI, how are they like moving around those like that space of like managing people's data and not getting away with it and not getting into like, serious legal issues around those lines?
Yeah. So you,
Yeah, we can take answers from John.
My name is John Kimani. I work at Google. I can assure you that I am not on the product team specifically, but we have very, very strict policies on data, and none of this training is taking place using your personal data. And James, who's coming next, will be talking a little bit about Google Cloud and all of that and how it's enforced. But basically, first and foremost, your private data is your private data. Models are trained on publicly available data. If you go on Google search and whatever you can find online is what is being used to train your data, if that makes sense. None of it is coming from your Google Drive or your Gmail. All right?
Can I just have a quick follow-up? So since we're getting to the age of like we want these AIs to be more useful to the people that are using it, and I feel like to train an AI model to be more useful to us, it needs to know me personally. For example, if we're talking about listening to music on Spotify, it needs to know my preference. It needs to be studying my data. If it's Gemini and I want Gemini to be able to assist me in my day-to-day work, it needs to know everything about me. And I think I saw on the last week Google was having a keynote, and then they were talking about how now Gemini can like access your repository on the cloud, and then it can help like a new developer to be able to contribute without knowing much about the code base. And I wanted to try that feature on my work stuff, but I was like, can I really, just give it access to the whole code base? I don't want to like expose that data. So how do you maneuver around those lines?
So there are two things there that you need to think about. So there's a foundational model, which is Gemini, right? So that model is trained to be multi-purpose. You can use it in different use cases. And the second step, once you have this foundational model, then you can bring it into products, right? You can either bring it into a Google product, or you can bring it into a product that's been built by you, right? And so once you start utilizing and leveraging these models in specific products, then there are very specific privacy policies that follow. Okay, so if you allow this model to be integrated, the Android Studio, for example, demo was fascinating for all of us, being able to comment your code as you go along, and you have this assistant that's following you as you write your code. Very useful for someone like me who writes spaghetti code. But all of this is based on, we have very, very strict policies around product use cases and models. And one of the things probably we should have mentioned is also just our AI principles as well. We want to make sure that any utilization is private, it's in line with what you expect. No surprises, right? And so all of this has been enforced. I know it's a big question. It's hard to answer in a very short period of time, but hopefully that helps.
Because luckily we're going to have those smaller sessions, so there'll be an opportunity to ask more questions. There'll be an opportunity to ask more questions in the smaller sessions, so I'll have to go to the next speaker, which is James in this case.
So don't forget your question, write it down somewhere.
Yeah, there'll be plenty of time. Also, there's a networking session at the end as well, so you could any questions that you have, our speakers are going to be able to assist. Yeah, so it should be quick. Okay. One last round of applause for Ngesa.
Great.
Yeah,
It's okay?
we can hear you.
Thank you. All right. So let me present my slide here. I think I'll present the entire screen. Great. Um, so in the next session, we are going to look at taking what Marvin has walked you through and seeing how we can apply it using Google Cloud. So we are going to be looking at Google Cloud AI platform, which is Vertex AI. But before that, we are going to look at the models that are available that you can be able to utilize, and that is Gemini and Gemma. So that's the agenda. What are large language models? I don't think I'll spend time there. I think Marvin has spent some good time explaining that. So I'll probably just go straight to walk you through the available flavors of Gemini as well as Gemma. And then we're going to look at Vertex AI Studio, which is Google's artificial intelligence platform on Google Cloud. And then we'll see how can you now deploy a model and be able to use it on an application. And in our code lab today, we are going to build an app that uses Vertex AI, and then it's able to access the Gemini model, and you can utilize it in your application. So those are large language models. I think, thanks Marvin for that detailed explanation of how they work, the underlying technology. You know, coming all the way from neural networks, transformers, encoder, decoder, and that is what enables us to have generative AI technology, which is able to generate text, images, or any other kind of media using LLMs. Now, Gemini is a large language model, and it's the most capable AI model today on Google Cloud. And it has unmatched capabilities for cloud-based AI projects. It comes in multiple flavors. The first one is Gemini Nano, which is the smallest version of Gemini. And this is a model that can be executed on a smartphone, on devices that are capable of that. For example, the Google Pixel, and I think some Samsung devices. And this model is built to enable on-device AI, empowering Android developers to be able to build generative AI applications for Android. Then there's Gemini Pro, which is the best performing model with multimodal features for wide variety of tasks for text, images, and image and reasoning tasks. And then there is Gemini Ultra, which is even more powerful than Gemini Pro. Now, Gemini Pro and Gemini Ultra are available on Google Cloud. You can be able to go and select the model like I'll show you and be able to create an endpoint or an API and start sending generative AI tasks to that model. So Gemini 1.5 Pro is very powerful. As you can see, it has a very large context length. It can ingest up to 1 hour of video, 11 hours of audio, 30 lines of code, 700,000 written words, as compared to other models that you're seeing there. So in a nutshell, there are many foundation models that you can utilize on Google Cloud. A lot of them are Gemini based, Gemini 1.0, Pro, 1.5, 1.0 Ultra, and then there are open source models, for example, Gemma models. There are other models that have been there before Gemini. For example, Palm has been there. It's been used via APIs for text generation. Imagen 2.0, which is an LLM that is able to create and edit images using simple prompts. There's Chap for speech to text generation, and Cody, which is a model that is built for code generation. Now, these foundation models are available on Vertex AI's Model Garden, and I'll show you how to access it. They're not the only models available there. There are other models that you can access, which are open models built by other people. for specific tasks. You can also be able to integrate Vertex AI with something like Hugging Face and be able to bring in your models from there. So in a nutshell, right now, Gemini models on Vertex, we have 1.0, which is generally available. It's the one that's recommended for production use cases. And it's available in different versions, 1.0, 1.5, Ultra 1.0. Access to some of them may be limited at the moment, but they're becoming more and more available as time goes. There's also a service on Google Cloud Vertex AI called Search and Conversation, and you can utilize Gemini Pro there. The pricing has been reduced, so for developers, it's easy to access these models at lower cost. And Pro 1.0 is still free for up to 60 queries per minute using AI Studio. If you want to know about pricing, it's available on Vertex AI Generative AI pricing section. Then we have Gemma. So Gemini is Google's model they built for LLM tasks, multimodal reasoning. Now, Gemma is an open model based on the same technology, but it's a model that you can be able to customize, contribute to, and use in your own other tasks. And it's built on the same technology as Gemini, but released as an open model. So at a glance, it's considered a fairly lightweight model, so it's easy to, for example, deploy. And it comes in two families, 2 billion and 7 billion parameters. And the same, as we are seeing, the same technology that is used for Gemini, which is closed and available via APIs, has been used to build Gemma, and it's released as an open model to developers. So there are some quality benchmarks that have been done on Gemma compared to things like Llama 2, Mistral. I know Llama 3 came out, I think, the other day. I would like to see the comparison there. But Gemma seems to perform very well when compared to these other popular open models. So as compared to the other Gemini models, you can think of Gemma as Google's open models built for the open community with the same capabilities that Gemini offers. So it's small, it's efficient, and it can be used for already defined tasks, like text-based tasks. So there are several ways you can deploy Gemma. One of them is you can deploy it on Vertex AI. And I'll show you how to do that. You just go to Vertex AI Model Garden. You look for the Gemma model. You say deploy, and then it becomes available. You can create an endpoint that you can interact with from Vertex AI, and then you can start sending it, tasks using whichever code library you're using, whether it's Python, Java, or just REST APIs. You can also deploy it on Google Kubernetes engine. So if you prefer to manage the underlying hardware for where the model is running on, it's possible to provision the model on Google Kubernetes engine. And it's just as easy, if you know how to use Kubernetes, just as easy as deploying another Docker-based image. Of course, for a model, you need to specify that you need some accelerators to be able to run it. But the same way you deploy an application that is Dockerized, create a deployment, create a service, you can do the same with the Gemma large language model on GKE. It's also available in all the popular AI frameworks, whether it's Keras, JAX, TensorFlow. I think the Google team has put in a lot of effort to make sure that the model is readily available and easy to use on all the popular AI framework that are out there. So if you're using TensorFlow, you're using PyTorch, you can easily be able to import or install and import Gamma and use it in your application. It's built responsibly. So I think, as John mentioned, Google has put in a lot of effort on responsible AI, and there is the responsible generative AI toolkit to make sure that these models are safe, and they're built in a responsible manner from the ground up. So, for example, if you're using Keras, that's how you can import Gamma in your application, and then very easily be able to send it some text for it to generate response for you. With those three lines of code, you're able to import it, send it a request, and get back a response easily. So those are now the models, Gemini and Gamma. Now, Vertex AI, as I mentioned, is the AI platform on Google Cloud, where you go to easily be able to do your machine learning tasks, whether it's generative AI tasks or normal machine learning tasks such as training models. The Vertex AI platform is the platform for that. And it's referred to as the Unified Development Platform for data science, machine learning, and now generative AI. It has quite a number of features. Key of them being able to easily build and prototype generative AI applications using Vertex AI Studio. And I'm going to give you a quick walkthrough of Vertex AI Studio. Another one is Model Garden, where you can go and discover models that are available, whether they're Google's foundation models or models from the community, and easily be able to deploy those models and start interacting with them. Because it's a platform that is built from the ground up for artificial intelligence, it reduces the training time and costs for you, because you don't have to spend a lot of time implementing machine learning ops in order to be able to do your ML tasks. So there's the Vertex AI Studio. Now it has multimodal capabilities powered by Gemini, and it's just a simple UI interface for you to interact with large language models. For you to select a model, send it a prompt, select another one, send it a prompt, and also be able to export that code to your own local development environment. It also makes it easy for you to tune models with your own data. If you're using a foundation models and you'd like to tune it with your own custom data, it's easy to do that. And now it supports multiple modalities. So you have models that can understand multiple modalities from text, images, and video. I've talked about the model garden. It's like a one-stop shop where you go to find models and be able to interact with them directly, tune them, customize popular open source models through, and then be able to access them via APIs. So I want to give you a quick overview of Vertex AI. So Vertex AI is available on Google Cloud. If you just come here and search for Vertex AI, you're immediately in the Vertex AI environment. Now, a lot of the times when you're on Vertex AI, you're doing experimentation with models, designing your prompts, and then you generate code or APIs that you can go and customize and extend in your development environment. So as you can see here, we have the Vertex AI Studio. Here you can be able to play around with models that are available from Google or models that you have provisioned yourself. It has multimodal capabilities now, with which is powered by Gemini. So for example, I can ask it a question based on an image. So I can give it an image and then ask a question for it to, do that with that image. So, e.g., I have this image here. This is an image of a product. So you can see it. It's an image of just a generic product that you can use to charge something on your car. So I can tell it, study this image, and outline the features of the product. Then export them to JSON. So that's a multimodal prompt. So it's studying the image, and then it generates a JSON output for me that contains the features it has gotten after analyzing that image. Yes. Now, on the side here, you can choose the model that you want to target. Right now, I'm targeting Gemini 1.5. You can also target 1.0, experimental, stuff like that. You can adjust the temperature, which is, zoom in. Oh. Okay. Yeah, so you can change the model that you want to use in your prompt. So right now they are these Gemini 1.5, 1.0, etc. And then, once you play around with your prompt, and you can see the responses are okay, and you're thinking, maybe I can have a user on my app be able to do this. You can just say, give me that code now, and then you have the code here, which is very simple. You just need, if you know how to use Python, you need to install the Google AI platform library, Vertex AI, and stuff like that. And it's as easy as that, sending the prompt and getting back a response. If you're using Node.js, you can get code for that, Java, and if you're not using any of those languages, you can use, you can just send a REST, a call to an endpoint, and be able to get back a response. Now, since Gemini is multimodal, it's also able to understand not just images, but also videos. So for example, there's a video here of Google CEO talking about climate change. So
whether you're in Brussels or joining
can't hear from
virtually,
there. Sorry.
we are grateful for your partnership.
So
Fighting
this is a
climate
video of
change
Google
is
CEO talking
humanity's
about
next big moonshot.
climate change.
And as with any moonshot,
Now,
we're going to have to
I can
answer
ask
some big
Gemini to
questions get
summarize that video with that prompt. And I submit it, and then Gemini starts working, going through the video, and then extracting and summarizing the content of that video. I think I need to reduce a bit. You can see. So if you are using large files, like videos, it takes a bit of time. As you can see there, it's saying you're processing a large file. This could take as long as 90 seconds. But it's going to analyze that video and give me a summary. So the video is about Google CEO Yeah, that's the summary for that video. So that's an example of our multi-modality of Gemini. Now, the other thing I want to show you quickly is the model garden, which is where you can now go and find open models, foundation models that you can deploy and use on your application. So you can see there are foundation models from Google, but there are other models out there. And all you do is, for example, if I wanted to find the gamer model, just search for it. I can, easily be able to deploy it. Just select the region, it will auto select the machine types for you and stuff like that. And you can also say, I want to deploy it to GKE, which is Google Kubernetes Engine. And as I was telling you, the deployment is very similar to a typical Dockerized application, only that you need to have additional information about the resources your model requires. So just to move quickly, if you come to the Code Lab, we have more examples of using Vertex AI, deploying a model. For example, I have a model here that I deployed recently. Once you deploy a model, it becomes available in your model registry. So I had recently deployed Llama 2 model, and if you want to interact with the model you've deployed, what you do is you create an endpoint. And once you create an endpoint, it becomes available in your online predictions section. Yeah, that failed. But this is where I can be able to interact with the model if the creation was successful. Now, in today's Code Lab, I wanted us to see how we can actually build an application that uses a generative AI model, in this case, Gemini. And one of the use cases for a large language model, specifically Gemini, is function calling, which is where you can supplement Gemini's response by giving it external real-time data. Now, as you know, a large language model, once it's trained, it usually has a cutoff time. For example, you've seen things like ChatGPT says, my cutoff date was last year. I think Gemini's cutoff date was October last year, something like that. But sometimes you want to allow your users to access real-time data and also provide them with, customized generative AI response. So function calling is a way of supplementing the response that a large language model gives you using external data that you can call from an API. For example, things like currency exchange, which is the example we're going to look at. It's usually, dynamic information that changes every day. So if you ask Gemini about the current rate of the rand to the dollar, it will tell you it doesn't know because it was last trained last year. But what if you had an application where you have generative AI capabilities, but also you want to augment the response using real-time data? That's where function calling comes in. You give the model a prompt, and then you program it in a way that it can be able to access an external real-time API, and then use that data to formulate the response it's giving to the user. So that's the code base, the Code Lab for today. I can see I'm being asked to end, but ideally we are going to see how we can use the cloud, the Google Cloud AI platform library, and also the Vertex AI libraries to be able to import a generative model, the large language model, in this case, Gemini 1.0, and then see, can we send it a request where it tells us, I don't have real-time information on that, and then how can we, supplement it with real-time information. So that's the Code Lab for today. I think I'll stop there.
Thank you very much. Thank you very much, James, for this really interesting talk. I do have space for 1 or 2 questions. So if there's a present question that you want to ask, afterwards we're going to have a really short break, and then we're going to go to the code labs afterwards. Do we have a question? I see a question at the back, and then a second question. So I'm going to... Okay, let's... Can you just pass the mic?
Hi, I'm Enoch. Just wanted to ask. So I saw you say you're pushing the figures about it takes in 1 hour of videos and all that. The video you just showed, demoed, was like 3 minutes.
Yeah.
Like what in terms of then me having an application that says that uses the model, and most of the time I am summarizing, say, lecture videos, like what in terms of latency and the time it takes to summarize, like how like, is there a way to optimize? Is it just because maybe right now it didn't it I don't know.
It was a short video, and that's because the platform on Vertex AI, the multimodal section, is meant mostly for prototyping and being able to understand how to interact with the model. Now, when you have large tasks that you want to use, obviously you need a lot of resources to deploy the model, maybe on GKE or stuff like that. So here, there is a limitation because this section on Vertex AI is mostly for learning and prototyping and being able to build a Gen AI application. But definitely, as advertised by Google, it can be able to understand 1 hour of video when deployed.
Okay, thank you. So I'll go to Sylvia.
Thank you. I'm Sylvia. I'm an app developer, and I'm curious about Gemini Nano. You mentioned that it's available, and I understand that's been pushed onto newer pixels for Google products, but I can't find any information yet whether it's available to us as app developers. Like, can we code against Gemini Nano, or can we push a model with Nano on a device already, or is that too early?
Yeah, and maybe John can also help me here. I think it's coming to developers.
It's not available. It's not generally available. So
Yeah.
you have to request to join the beta for them. They give you. I tried it and they asked me to fill out the form.
But that means it's coming.
It's coming.
But it's hardware dependent. So the Pixel 8 is the one who currently supported. So sorry, you have to buy a new one.
Yeah.
Okay. Okay, no.
Yeah. Thanks for helping me there. Yeah.
Okay, let's have another round of applause for James. Okay. So we're gonna just take a small, like 5-minute break. You can go to the bathroom. You can just stretch.
Before break, how many of you are interested in Vertex, Gemini on web, Python, and Node.js? Show of hands. How many of you are interested in Gemini on Flutter and Android? Make my job a lot easier. Okay, just 2 of you. What was the other one again?
Web and cloud. I
Is
think.
it possible to do like patient? Because some people are probably interested in Vertex, some people are probably interested in.
Oh, we can do one then.
Okay. Cool.
Yeah.
So just have your laptop and your plug points all around. If you need to, don't be like us this morning. Charge your laptop so you can put the alarm. So yeah, you can use the restroom when you come back in. You set up your computer and get started.
Also, there is Wi-Fi as well. So the Wi-Fi code is here. So when we connect, but then we're gonna show it on the screen. So don't worry about it.